All right, PCH, welcome to day 2 of AP Calculus. Our first lesson that we talked about was finding and evaluating limits from graphs. Well, now we're going to talk about trying to evaluate a limit from a table, because we're not always going to be given the graph. And so if we're looking at the top of our notes here, saying, hey, consider this function f of x, which is a rational function, and we know that there are different key features that we can come up with for rational functions, some crazy things going on there. And it wants us to complete the table below to find the limit of f of x as x approaches 3. Now, when we are talking about evaluating limits from tables, most of the time, the value that they're asking you to look at, in this case as x approaches 3, there's something special and specific and interesting going on at that value most of the time. And so the first thing I want us to figure out is, hey, when we're considering x equals 3 for this function f of x, what's even interesting about x equals 3? What is happening there? And in order to have us do that, the first thing I'd like for you to do is go ahead and factor f of x. What we notice when we factor f of x, we factor the denominator, is that we have a factor x minus 3 that is in our numerator and our denominator. And when that is the case with a rational function, as we learned in try 1 of PCH, those factors cancel out, and what we have on our graph is a hole at x equals 3. And so that's the special funky thing that's happening at x equals 3 on our graph. And we know that when there's a hole, right, if we're thinking about a graph, and this isn't going to be perfect, but let's say, we have some rational function. A hole is just going to be an empty circle on our graph. And we know that if I was going to say, hey, if I ask you for what f of 3 even is, well, it's going to be undefined. In this case, because we have a hole, if we were to plug in 3 into our function, we'd be dividing by 0, and we can never divide any fraction by 0, specifically a function like we have here. And so if we're thinking about filling out the table and we say, hey, f of 3 is undefined, that does not mean that the limit does not exist, right? We talked about this yesterday. When we are talking about limits, we're talking about the y value that our function is approaching, not necessarily what's actually happening there. And so the fact that f of 3, the function f at x equals 3 is undefined, that doesn't mean the limit doesn't exist. And so what we need to do is go ahead and plug this into our graphing calculators. Obviously, I know that a lot of us don't have graphing calculators, and we will do our best to practice this during class. Calculator skills are a very, very, very important part of calculus, and so I want to get us started on that right away. So again, once you walk into AP Calculus next year with Unit 1 under your belt, you'll feel pretty familiar with doing some really cool things on your calculator. So what I went ahead and did is I'm going to graph this function so I can see what it looks like. And we will talk more about this as well, but I want to make sure that the entire numerator, which is x minus 3, is being divided by the entire denominator, x squared plus 2x minus 15. That's why I put both of those things in parentheses, so that when I graph, I see my function here, and I notice that there's a little bit something interesting happening over here as well. And based on what we know from try 1 of AP Cal, or of PCH, right, that vertical asymptote, I bet you, is coming from x equals -5. That is what we're seeing on the graph. That is no surprise to us. And so we've talked about this before, but if we go to second table, right, we can look at the table of different x values and the y values that they are defined for on our graph. Right now, the calculator auto-generated each of my x values and then, of course, my y values as well. But if we're looking in this table, right, I want very specific x values that I want to have in my x column here so I can find my y's. And if I'm looking at my table, it matters to me, of course, when we were talking about limits, right, I'm picking values that are really, really close to 3 on either side. So as we approach 3 from the left, that's what these values are going to be on the left. So I'll say left, as well as values that are approaching 3 from the right. Those are the values we want to focus on. And you'll notice that we get really, really, really close to 3. We're at 2.999. 3.001, very close to 3. And I want to make sure that I can find those in my calculator as well, because we won't always have a graph. And so I just want to show you this calculator skill. If we go to second window, which is going to take us to table setup, our table, we can go ahead and just start it wherever. But the main thing for me is that I want to go down to the independent variable and say, hey, I want it to be able to ask me, like I want to tell it what I want to put in there. Because the independent variable is my x. And so once I have that set, I'm going to go to second graph, which will send me to table again. And I'll notice that my entire x list is empty, meaning that I can type in whatever I want. And so I'm going to go ahead and do that. Start with 2.9, and when I press enter, it's going to give me a y value. And so I'm going to go ahead, I went in and typed in the rest of my x values that I cared about. And if you have your own graphing calculator, absolutely you should be following along with me, practicing this, getting you that muscle memory, those calculator skills built into your repertoire. But if not, we will practice together. And something we see is that when we're plugging in these x values, we're getting our different y values over here in blue. And something that we see when we plug in 3 for x is we get an error. Well, that's not a surprise to us, because we already said, hey, we know, because we're excellent PCH students, that for this function, there is a hole at x equals 3. I know my function's not defined there. I know why this is telling me that there's an error. I don't need to be shocked about that in any ways. But as we're looking at this, right, and we're thinking, hey, as I am getting closer and closer to 3 from the left, what are my y values approaching? We're at 0.126, 0.125, 0.125. It looks like we're getting close to 0.125 as we approach 3 from the left. If we do the same thing from the right, 0.123, 0.125, 0.125, also looks like I am approaching a y value of 0.125. And based on what we learned yesterday with the limit existence theorem, if the limit from the left is equal to the limit from the right, I want you to tell me what that means, specifically for this limit we have here, this third limit. Yeah, according to the limit existence theorem, if the limit from the left is equal to the limit from the right, that means my general two-sided limit, in this case, as x approaches 3, it exists and it is equal to that same value. So the limit as x approaches 3 of f of x is 0.125. And again, we won't have our calculators, but just for sake of looking at this and learning, if I go ahead and click on trace, I notice like as I move to the right and as my x values, which you can see in the bottom left corner of my screen here, as they approach 3, what is my y value doing? It's doing exactly what we found in our table. It's getting closer and closer to 0.125 until I hop over 3, and as I get further away, right, we're going a little bit further away from 0.125, following what I found in my table. And of course, if we were to do second trace to get to calc, and we look for a value, I'm going to click enter, and I type in 3, it's not going to give me anything because there is a hole there. And so this is a fantastic example of a situation where even though the function value doesn't exist, f of 3 is undefined, the limit as x approaches 3 of f of x, it exists, and it's 0.125. All right, nice work, PCH. Day 2, done. See you later.